courses in mathematics. And if you're going to be serious to combine linear algebra and this part of mathematics together for future, something to doing, in quantum mechanics, etc. So you need this type of arguments for the derivative. Okay, so basically, what is the derivative? You see, we talk about partial derivatives, but we didn't actually, and partial derivatives are nice, but they are not going to be enough. Okay, so we get back to the actual derivative, how we're going to take care of the derivative of the function. So this is going to be section 13.4, and we would like to see how we're going to define the derivative. Okay, would like to define the derivative of a function of several variables. Okay, of a function of several variables. That's it. So you see, when we say, again, you go back to see what you did in calculus 1 for the function of one variable and try to copy that one for the function of several variables. Okay, so recall that what we did before. Recall that if the function y equal to the f of x is simply differentiable, is differentiable. Okay, if this is going to be differentiable at a number x equal to the a, then the derivative of the function would be, okay, then f prime of a is going to be the limit. Okay, it's going to be limit of f of x minus f of a over x minus a, x goes to a. This is the definition of the derivative of a function of one variable. So if you want to copy this one, let's see how far you can go and what's going to be the difficulty. If you want to copy this one, so you have to go with the function if z equal to the, okay, equal to the f of x comma y. So you can say that is differentiable. If this is going to be differentiable, your point is going to be x0, y0. Okay, then you expect to write the similar thing. So you may expect to write the f prime of x0. y0 is going to be the limit of same thing. Okay, f of x comma y minus f of x0 comma y0 divided by the difference between, x. This is x at the point that we have is going to be xy, if you like, minus x0 y0, if you like. You see, when x comma y goes to the x0 y0, you expect to be able to write this, the same thing that you're going to hear. Let's see what's going to be a difficulty to take care of it. The first difficulty is going to be the shape that you have. Everything must be in proper position. You see, in the case of the real numbers, this is a real valued function. This is a number, and this is number. So when you divide it, makes sense. But over here, the top is a real valued function. So the top is numbers, but the bottom are vectors. Okay, so the top, the difference of two vectors would be a vector. So you have a quotient kind of, you get a number on the top, you get a vector down the bottom. It doesn't make sense here. Okay, then you will have difficulty in describing this quotient, and if you want to continue with the notion that you have in calculus 1. Okay, because you know now the definition of a limit. So even say the limit is f prime, this means the limit of the difference. The limit of difference goes to 0. And it makes sense because it's the numbers, but the difficulty is going to be that quotient that you have. Okay, so this means you can't do it. You cannot just go on as you did before. So you have to repair it, if you like. In the history of calculus, they just find different way to describe it. And one way that we can describe it is the fact that you can look at this, okay, to see what we can do about this quotient. Okay, the difficulty is this quotient that you have. So if you just continue with this is the one that you did in calculus 1. So if this is going to be true, then the difference, you see the difference, f of x minus f of a over x minus a minus f prime of a, if you like. You see f prime of a. The limit of this difference is going to 0. Limit of x goes to a. Okay, this goes to 0. And if you stay with this limit, take a common denominator. So this means the limit of x goes to a. The common denominator makes sense, so it's going to be x minus a. Okay, and the top would be f of x minus f of a minus f prime of a times x minus a. Okay, so look at this one. This is equal to the 0. Okay. So in a language of calculus 1, if this the top is going to be 0, so this means okay, this means the top of this fraction, if you like. You know that if you use the definition of a limit, this basically means that the top is going to be approximately 0, if you like. Or, you know, we can, this means the absolute value of f of x minus f of a minus f prime of a times x minus a over, if you like, x minus a. This would be approximately 0. If this is going to be approximately 0, so the top would be approximately 0. You see f of x minus f of a minus f prime of a times x minus a would be kind of approximately 0. And if you remember from calculus 1, so this means your f of x would be, so what we do in calculus 1, you see that the top. So let's, what we do in calculus 1, this is just the equation of a tangent line, if you like. So in calculus 1, this notion over here, we refer to this L of x. Okay, let me just go one more step. So the step is going to be f of x would be approximately f of a plus f prime of a times x minus a. It's what we do in calculus 1. This is just the equation of a tangent line. So in calculus 1, we call this one L of x, if you like. And then we say that L of x is approximately like f of x. This L of x would refer to it as, okay, just remind you, it's called the linear approximation. Linear approximation. Linear approximation of a function f at a. Do you remember this one from calculus 1? This is the equation of a tangent line and nothing else. So this means if you have a, you see, this is the interpretation. The interpretation is that if this is going to be, you know, a kind of a curve that you have, and this is going to be the point A. You see, and this is going to be your tangent line. This is your tangent line, which is the same as the L of x. So if you get a point X, you see if you get point X, the value of the function, this is going to be L of x. That's going to be f of x. The red one is, okay, this is going to be the f of x. But if you get it from the tangent line, this is going to be L of x. Okay, so the largest one is, this is going to be your f of x. And the green one is L of x. As you can see, they are close to each other. So this means if you're getting closer and closer, you see if you get closer and closer, then the value of your function can be estimated by the value of the tangent line. This is the one that we call it tangent line approximation in calculus 1. And we use it in order to estimate the value of the function. Okay. So that will tell us something that if you want to correct, one way to do it, one way to do the derivative of this function is to look at the similar thing here. Look at this one. Remember, we did have a difficulty for this quotient. So if you consider exactly the same thing, you see if you find the limit of the difference, and you do the same thing over here, you will arrive at the conclusion of something that would be useful to be able to get the domain of your function. So I'm going to copy this, whatever I did, but I copy it for this part. Then it gives an idea for the differentiability that we're going to know. We're going to use it. Then I give one example on this. Okay, so that gives you the connection that if a function is going to be differentiable, so far, again, they are all motivation. So far, this means, so these are just, just getting the motivation. So if, okay, f prime of x0, y0 exists, then the same thing that we did over here, see? The difference between the derivative f of xy minus f of x0, y0, okay, divided by xy minus x0, y0 minus f prime of x0, y0, this must go to 0. Again, if you find the common denominator as we did it for the other part, it's going to be exactly the same thing. You see this one? Of course, the bottom one is a vector, but it does make sense. You get f of x comma y minus f of x0 comma y0, and this would be minus f prime of x0, y0, times it by the difference between the vectors, xy minus x0, y0. You see, that goes to 0. And if you take that top out, that would be very much similar to the one that we did for the function of one variable. So this basically means that if the function is differentiable, so if f is differentiable at what? At x0, y0, then same thing that we did for the other part. That top must be 0. You see f of x comma y minus f of x0, y0 minus f prime of x0, y0 times it by xy minus x0, y0. That goes to 0. So it's going to be similar thing that, if you take this one out and talk about it as L of x comma y, so you arrive at the similar thing, that the conclusion is going to be the value of the function should be able to estimate it by the, okay, a kind of linear approximation they're going to have. These are all motivations. So this means if f prime of x0, y0 exists, then the values of f can be estimated around the point x0, y0 by its linear approximation, by its linear approximation, which is L of xy. That gives you the hint. You see, if you want to do a research, it's the way you do it. You check to see what's going on. Can I repair it? Can I put them together? What do I need in order to be able to do it? So that gives us a plan. Now we're going to, to operate it if you like. You see this type of derivative, if you like, that we are going to use. It was used. I'm going to write it down officially for you. It was created by by a French mathematician. We have two different. We have different types of derivative, if you like. But if you are interested, serious about getting more involved with this type of ideas, you can check for the name. The name is Frechet. That's a French name. Frechet's derivative. You see, this is this argument that I did. You can put them together and get the differentiability. So in the language of the Frechet, this means a function f is differentiable. F is differentiable. Okay, at this very brief form of this, at x0, y0, if this limit is 0. If the limit of, okay, because of the difficulty of those dividing, we divide the norm. You see the norm of f of x comma y minus f of x0, y0 minus just that the derivative that we have, f prime of x0, y0. It's very, I write it down in the form that, it makes sense just for this part. If it's going to be xy minus x0, y0, the norm of the top divided by the norm of the xy minus x0, y0. This limit would be 0, of course, when xy goes to the x0, y0. This is called, in your book, they don't talk about this type of things, but if you like, the origin of the argument that we're going to simplify in a minute is what we call Frechet, okay, derivative. Of course, when you change the numbers, it's going to be different. If you have done linear algebra, the derivative of the function is a kind of linear operator. So there is going to be a linear operator that we call it f prime, and then you'll be able to do this type of things. But the one that we are going to use in this course is, if you want to check the function is differentiable, of course you have to check this one, which is not easy. So what else can you do? You can prove the function is differentiable if you can prove this one. So instead of the proof, we are going to use this one as a definition. We say that a function is differentiable at x0, y0 if linear approximation of the function, okay, if the function, the value of the function can be approximated by L of xy, approximated by its linearization. We take this one as a derivative of the function, and that make it easy for us. So as you can see, we can talk about the differentiability, but if you want to find it, it's not easy, okay? So you have to use something else that we're going to provide you with that something else right away in a minute. Any question? So just give some thought, for this type of idea. You see, I have difficulty if we have this difference only, because that's a vector, the top is a number, we cannot divide it, so we put the norm on the top and the bottom. When you put the norm, number, so you can divide two numbers, so you don't have any difficulty. Okay, so what I'm going to do, I'm going to start over, give you as a definition. I define a function to be differentiable if this is true. Then that would result in a theorem that make it easier for us to be able, to take care of it. It's quite interesting subject, of course. You can extend it to any vector space, and you can talk about differentiability on the vector spaces, okay, from the linear algebra. And there are some other part. This is Frechet. There is another one called theory. If you are serious about mathematics and you would like to get something, I've given this one as an honors program. a number of the times to the students of this course. Okay, and if you would like to get more information, this is a very good one and easy to read. You see, this is from this is Mathematical Association of America. This paper, search internet from your college site, you should be able to get it. I will post it on Canvas if you would like, you have to read it. That give you an idea of two different types that we define this derivative. Frechet is the one that I talk about it. The other ones call it Caroteodori. It's going to be used, in advanced mathematics. If you are a math major, of course, you're going to see it. I've given several talks on this. They are on internet. You can check it. But if you would like it, this is the way they compare it, the derivative, okay, together. It's a very nice paper. And they just keep going and proving all the theorems that you have. We're not going to do this step. The basic property, addition rules, the product rule, chain rule, in this category. This category would be used for if you know a little bit of linear algebra for future, okay? But the way we are going to use it, we put it into the format of this course. But it would be nice, if you like to get it, okay, that's it. I posted on the Canvas, if you want to see the history of this type of definition, okay? So, because I didn't want to start it right away, so you won't get it. So what we're going to do, we are going to define this linear approximation. We are going to a little bit change it to the format that we can do it. We write it down in terms of the partial derivatives and be able to do it, okay? So that was the motivation. So I need this. I need to create the linear approximation for a function of two variables to be able to get the definition, okay? So let's go back. That was history or motivation, like a research. So we research it and we find out that we have to extend the notion of the linear approximation from calculus 1, okay? Sometimes we call it tangent line approximation. So what is the version of the linear approximation in higher dimension? Linear approximation. And sometimes we call it tangent line approximation. That's it. So I do it the other way around, if you like. I motivate it, then I can do it. Now, let's see. Very similar. So we plan it. So this is the way we do it. We do your research. So you got the tool, so you have to organize the tool. There you are. Suppose z equal to f of x comma y is a given function. Given function on the domain. It can be done for two variable or three variable function of 2 or 3. We go the 2 first. Okay, on the domain D, which is a subset of R2, and we have a point. And A comma B, we do it in two-dimensional. Is a point in D, such that, look at this, such that partial derivatives f sub x, partial derivative of f respect to the x, at the point A, B exist, and partial derivative respect to the y at A comma B exist. I'm going to switch that f prime that you saw. I switch it to the partial derivatives because I don't have the f prime, you remember? I don't have the f prime, so I switch it into the f double prime, okay? So these partial derivatives exist. Now I can bring the linear approximation. Okay, that's it, the linear approximation. Linear approximation. Linear approximation of the function f at the point A comma B is given by, there you are, L of xy, L of x comma y Remember, the first part was the value of the function. So it's going to be value of the function f of a comma b. In the second part, you see it was f prime. Look at this one. Value of the function f prime times x minus a. We don't have the f prime because the function of two variables. But instead of f prime, I switch it to the partial derivative with respect to the x. Okay, so it's going to be partial derivative respect to the x, okay, at that point f prime, at a comma b. Simply I multiply by x minus a. Then I continue the partial derivative with respect to y. Partial derivative with respect to the y at a comma b times, this is partial with respect to the y times y minus b. Okay, this is going to be our linearization. So we just extend that notion, we copy that. Okay, if the function is going to be a function of three variables, you continue. Partial with respect to the x, partial with respect to the y, partial with respect to the z. Okay, so I create L of xy. So it's going to be linear approximation. Now, what else? In the function of one variable, remember, when it is differentiable, I prove that when it's differentiable, then the linear approximation, the value of the function can be approximated. Differentiated. Now I'm going to use this one as a definition. Say what? I say, oh, if the function is differentiable. Okay, so I say that a function z equal to f of x comma y is said to be, if you use the Frechet, it's going to be the same thing, is said to be differentiable. So look at this, just use this one as a definition. So the function is said to be differentiable at the point a comma b if, look at this, if the value of the function can be approximated by its linearization. You see, if this is going to be true. If this is true, where? Around that point for all, okay, for all points x comma y near a and b. Exactly the same thing you did with it. You see, that's exactly the one that you did. So I just picked this one as a definition of a differentiability that you're going to have. It's the same, it's going to be the same thing. So we say that f is differentiable if we can prove this one. You see, in the case of the function of one variable, we did have the differentiability. F was differentiable, we proved that, the value of the function can be approximated by the value of the tangent line. So over here, we take this one as a, as the definition of the differentiability. Of course, this is not going to be easy sometimes, but we have a theorem that we are not going to prove it, but we're going to use it. Look at this. It can be proved. It can be proved, if you are going to be math major, you can prove it. It can be proved. You need a mean value theorem. It can be proved that if the partial derivatives functions, because you want to use the mean value theorem, partial derivative function f sub x and f sub y are continuous, are going to be continuous at the point a comma b, then f is differentiable. Then f is going to be differentiable in the sense of the differentiability. You see, we talk about differentiability, we don't talk about defining it. Okay, it's going to be differentiable at a comma b. You see, So this means if you just check the continuity of these functions, okay, if you check the continuity of this function, then automatically your function is going to be differentiable. If your function is going to be differentiable, then the function can be estimated by its tangent line. Okay, so this is the way we cut it short, if you like, in a case, because it's calculus 3, it's not a mathematical analysis course. If you are going to be, of course, in that course, we prove all these, okay, in details. But that will help us to be able to cut it short, okay, get a source of differentiability without having to prove the Fréchet's concept, but that would be fine for us. So your first question, first job is going to be a function would be given, and you want to see if that function is differentiable. So far, just differentiable. They are not going to ask you to find derivative of the function because you can't do it. Okay, so this is going to be our first example. Any question? So give me an example as we go on, then we come back to it again, explain it if you need it. So you see, this is your first problem in your book. They ask you to show that. It will be combined with something else in a minute, but this is going to be so far. Show that f of x comma y equal to the x squared y cubed plus x sine y. They ask you, show that this is differentiable. Is differentiable. Just check if it is differentiable. Okay, so checking is you just check to see if the partial derivatives are continuous. Okay, so we check. Solution is going to be find the partial derivatives function. Are you ready? Easy to find. F sub x at xy. Keep the y constant, differentiate respect to the x. This is it. Derivative 2x, 2xy cubed, 2xy cubed. Respect to the x, derivative of x is 1. 1 times sine y. It's going to be just sine y plus sine y. That is derivative with respect to the x. Nice, it's continuous. They are all polynomials. Okay, is continuous. Is continuous in the domain which is on R2. It's a function of two variables. Okay. Similarly, find the derivative of f sub y. What is f sub y? X comma y. Differentiate. Respect to the y. 3y squared, 3x squared y squared. With respect to the y, sine, cosine, plus x cosine of y. Nice. All polynomial trigonometric function is continuous. It's going to be continuous on R2. That's it. The partial derivatives are continuous. So function is differentiable in a sense of the differentiability or just a Fréchet one. Okay, so this is it. So since both of them, so therefore f is differentiable. Differentiable on R2. And then do that. So far it's differentiable, okay? So then you learn how to differentiate it later. Any question? So this is one way to do it. Now, the other way is, the other question that you have to answer so far is this one. Since it's differentiable, like calculus 1. If it's differentiable, so we can find a tangent line approximation or linear approximation. And they may ask you to estimate it for us. Okay, in calculus 1, remember, we give you a question like finding and use linear approximation to find the estimate for the square root of 16.2, 16.4. Then you estimated around 16, radical 16.2, of course. So it's going to be similar one over here, but with 2 or 3 variables. Okay, so one of them would be given to you next test and get quite a lot in your book. So let's see what's going to be kind of application or other version. Then we come back and we discuss the derivative more. So you get a number of these type of problems. Linear approximation one. So this is how, in the previous problem, you just check the differentiability. You are going to do more here. So what's the question? The question is, would like you to show that. Show that this function f of x comma y. This is two-dimensional version of this problem from calculus 1. Okay, the square root of x squared plus y squared. In calculus 1, you did have radical x only. We want to show that this function is differentiable. Means you have to find the partial derivatives, show that the partial derivatives are continuous. They want to differentiate it at one point is given to at what? At the point 3, 4. 3, 4 and the price. And find its, I just use this expression, linear approximation. Sometimes you say linearization, same thing. It's a linearization. Okay, at 3, 4. Okay, this is it. To use it and use it to approximate, to estimate this value f of at point 3.04 comma 3.98. That's it. So on the test, we may not give you this, these functions sometimes. I explain. Let's do this one first. To get this is. So they may not give you this 0.34. Then you have to guess it yourself. And to guess, you have to pick something nice around this. Okay. So something nice means you see 3 is close to 3.04. So you pick it at 3, and this is close to 4. So you say, oh, I'm going to find the linearization at 3 and 4. They are nice because 3 squared would be 9. 4 squared would be 16. 9 and 16 would be 25. Radical 25. Okay, so this is the way it's going to be. It's going to be given to you later on. And we have a couple of them to practice. Okay, there you are. This is a full course so far. Everything we learned so far, we have to apply it. First, differentiability. You have to find partial derivatives and show that the partial derivatives are continuous. And then you need the partial derivatives to do the second part. Okay, there you are. The function. Well, I want to differentiate it, so we have to rewrite it. F of x comma y is equal to x squared plus y squared, everything to a half. Differentiate with respect to the x. F sub x at x comma y. You know that you have to apply the chain rule. You bring the half one down, 1/2 x squared plus y squared, everything to the negative half, and times u prime inside respect to the x. Derivative of x squared will be 2x, and derivative of y squared is 0. So simplify it, this 2 would be out. So this is going to be x. You bring that down. So radical x squared plus y squared. Okay. You know that this function is going to be continuous if the denominator is not 0. So this is continuous everywhere except at 0, 0. But you wanted at 3 and 4. So at 3 and 4 is nicely continuous. Okay. So it's continuous. It's going to be continuous at 3, 4. Because the only difficulty is going to be 0, 0. You don't have it. Okay, so there's going to be continuity of the first partial question. Check the other one. Similarly, that give you, again, you get the 1/2. You get the x squared plus y squared to the negative 1/2. Derivative with respect to the y would be 2y, of course. So the 2 and 2 would cancel out. So we get the y on the top and the radical x squared plus y squared. Same thing. The denominator would be 0 at 0, 0, but you have 3 and 4. So E is continuous. E is going to be continuous at 3 and 4. So the partials are continuous. So therefore, the function is differentiable. Okay, so according to the argument that we did, therefore, f is going to be continuous. Sorry, differentiable. It's going to be differentiable at 3 and 4. Any question? So as we build up this one, differentiability would be coming if the partial derivatives are going to be continuous. Okay, as we talk about it, this application of the mean value theorem can be into it. Okay, but now they ask for the linearization. So f is differentiable, and if you like, when it's going to be differentiable, you know that the function, the value of the function can be estimated. Is going to be, can be estimated by its tangent line approximation, of course, if you are going to be only around, okay, if you're going to be around 3 and 4 in this case. So you find the linearization, then you can drop, you can, and the number that you have are close because you have 3.04 and 3.98. Okay, so you have to find the linearization first. Any question? Linearization, the formula. L of x comma y is equal to at 3, 4. So it's going to be f of 3, 4 plus partial respect to the x at this point. 3, 4 is respect to the x going to be x minus 3 plus partial respect to the y at same point, but you're going to have a y minus 4. This is going to be your linearization at that point. Any question? So you have to find this and bring it back. When you got the partials, you can find the value of the function, the partial at 3, 4, 3, 4, then come back, write it, and that would be the estimation, okay? And so I'm going to find f of 3, 4 first. This is it. What is going to be f of 3, 4? F at the point 3 and 4. Go to the function, substitute. So that gives it 3 squared and 4 squared. So it's going to be radical 9 plus 16, radical 25, which is 5. So that's going to be 3 and 4. F of the 3 and 4, then partial derivatives. F sub x at 3 and 4. So the top was x, which is 3. The bottom one is the same as this one. It's going to be 9 and 16. So this is going to be 3 over radical 25. And that gives it 3/5. Okay. And similarly, partial of y at 3 and 4. Okay, it's going to be similar one, but it was y, so it's going to be 4. We get a 4/5. It's the same thing. So that gives you 4/5. Don't use decimals at this level. You can use the decimal later, not now. Okay, just put them together, substitute in this formula to get your linearization, then you estimate it. Okay, any question? So we go back to the formula. Remember, the formula is this one, plus, plus. It's not minus. Some people, they write minus. We're going to use this one exactly as in calculus 1 later on for the tangent line. Okay, so we're going back. I substitute here to get the linearization. So if you substitute, you get L of x comma y is equal to value of the function is 5 then partial derivatives are going to be 3/5, okay, times x minus 3. Then the second one is going to be 4/5, okay, times y minus 4, okay. It can be simplified, but since you want to estimate it, you just keep it as is. Okay, this is going to be true. But the conclusion that any question, you have to do your estimation. So now you know that f of the value of the function, f of x comma y, is going to be almost the same as the linearization. Of course, if the numbers are going to be close, x must be close to 3 and y must be close to 4. And the number that's given to you is the same thing, satisfying. So f of, you want to find the 3.04, okay, and the 3.98. So it's going to be close if you just go into this calculator, substitute, simplify. So it's going to be 5 plus 3/5. Okay, substitute for x, it's going to be 3.04 minus 3. And this is going to be 4/5. And that would be 3.98. Okay, you just simplify it. So this is going to be 0.04. And oh, I'm sorry, I missed here. It must be minus y, which is, this is minus 4. 3.98 minus 4. So the difference is going to be negative here. So it's going to be negative 0.02. Okay, you simplified using calculator to give you the result. So this is going to be, okay, so it's going to be approximately 5 plus 3/5 times, just repeat it, but use calculator right away. So it's going to be 4/5, and this is going to be negative 0.02. Okay, so if you use calculator, this number would be almost like 5.008. So the value of your function f of 3.04 comma 3.98 is going to be almost 5.008. That give you the final answer. Okay, you have to check it with the calculator and show it on the test that it is the same number. Okay, so just use some calculator to get these numbers. So calculator result, calculator. So, just go to the calculator, direct substitution. I just, you don't have to write down, of course. I just show you how we do it. It's going to be 3.98 squared, the value of the function. Okay, there you are. See if I can do it. So I have 3.04 squared plus 3.98 squared. So the result of my calculator is this one. Okay, 0.00819. So that means I did a good job. Okay, they are very, very close. So the result of the calculator is 5.00819. So just, quick showing that you are going to arrive at the same number. Okay, and on the test, they give you the answer because they give you one of them. And they ask you to compare your result with the result of a calculator to get these numbers. Okay, any question? So it can be done with the function of 3 variables. Okay, we have it, in your assignment. Just I give you a remark to keep it because we don't have example on that one here. So the remark is going to be if your function is going to be, okay, so if we call the function w is going to be f of x, y, z. Okay, this is going to be is differentiable if you like is going to be differentiable at the point which is ABC. Okay, this time is going to be in the domain, in the domain D in R3 this time. Then the linearization is going to be this one. Okay, it's going to be f of x, y, z is going to be, can be approximated. Of course, if your point going to be close to the ABC, and this is going to be your linearization, okay, where the linearization x, y, z, you start with the value of the function again, it's going to be f of a, b, c, then those partials, f sub x at abc, times it by x minus a, then f sub y at abc times it by y minus b, and f sub z at x, y, z, if you see it, and that's going to be z minus c. That's going to be the one. There is a version, we are going to use it later on when we get more involved. We take this one separately and talk about those, tangent plane later on. But you have to know it because we may give you a three-dimensional type, and the situation is going to be very, very similar. Okay, so this is how we, we stay with our plan now. So we just use that linear approximation property to be able to get through the derivative of the function. As you can see, these examples are nice. These examples confirm the differentiability of the function. But the question is going to be, how we're going to write the derivative of the function? Okay, you would like to have something like in calculus 1 to be able to find the, use different formula to get the derivative. Okay, so what we can do is we can go back to the calculus 1 and remember, we can have a differential of the function. And in science, in application, mostly and even in geometry, we go with the differential. So what we are going to do again, we're going to get help from the calculus 1. So we go back to see how did you define the differential of a function, differential of the variable, okay, y. And then we are going to extend that one to the calculus of a function of several variables. That will take care of everything for us, okay? As soon as we set up the differential, so we can bring all the formulas that we did before, okay? So going back to the calculus 1 to see what you did with the function of one variable, and it's differentiable, and come back. Okay, any question? So far what you did is good, is very good, because you just motivate the definition and you bring something that makes sense. So what you want to know, to put it into format that can be applicable in science. So what is that? Differential. Okay, it's a differential of a function, but in your book they call it total differential. It's the same thing that we're going to have. Okay, so question f sub z, what I did, maybe a misprint. Oh yes, you are right. Anyway, at the point, you're all at the points A, B, C. Yes, you are right. This is A, B, C. Okay, A, B, C, it's f of z at A, B, C. Z minus C, thank you. Okay, these are all the coefficients are constant. Okay, like the slope, like the slope. Thank you. Okay, so let's see, make it practical to be able to do it. So the practical one is go with the differential. Okay, it's a differential of a function, but in your book they call it total differential. It's the same thing. So it's going to be total or just differential. Differential of a function of several variables, of course. Okay, just recall what you did in calculus 1. We bring it back. Okay, there you are. Recall that function of one variable. If y equal to the f of x, remember, is differentiable. Is going to be differentiable. Then we can define the differential. Then use the same idea of those estimation that we did. Then the differential of the variable y, or of y, of f, y, or f, doesn't matter. Remember, is denoted by differential of the y, and is defined by, this is it. Differential of the y is simply derivative of the f times d of x. Remember, this is where we define the change in x, change in y. You start with the slope, rise, run. Then we want to estimate it by the rate of change, just the way we do it. And remember this equation, we refer to it as a differential equation. Okay, differential equation. That was the one. Okay, now we can copy this one. We can copy going to the function of several variables. So for the several variable, we switch this derivative of the function into the partial derivatives. Okay, so this is three-dimensional copy, HD version. So the HD version would be if z equal to the fx. We know that if this function is differentiable in partial derivatives are going to be continuous, okay, or if the partial derivative is continuous. So now if this function is differentiable in a sense that we talk about it, sense of the Frechet. Okay, so if this is going to be differentiable, then now the differential of the f, they call it the total, or just differential. Total differential. Okay, differential of the function of z, or of the function. Okay, differential of the function is going to be, is again denoted by same thing, d of z, differential of the z, or simply df, differential of f, and is going to be defined by, same thing. You see, differential of the z is going to be equal to, now the first variable is x, so it's going to be partial derivative of f sub x times the differential of the x. You continue plus differential of the derivative partial of the f respect to the y times the differential of the y. You see, that's going to be the version that you have. So some people like the other type of notation. We did have various notation for this one. So, or this is another notation. dz is going to be equal to, remember, round f round x, that's a partial, times the dx plus round f round y times dy. Okay, both of them are going to be the same, but it's going to be used in different places. That's it. So this is going to be differential of the function. You see, instead of the derivative of the function, we define the differential. Easily can be calculated. Okay, so we use the dz or the df from now on, and then we extend whatever we did before. You see the version that, for example, if the derivative of the function is 0, then we say the function is going to be constant, but over here, they are going to give in different format. Later on, you will see it, different names. And it would mean something if you use it in physics, okay, geometry, okay, mechanic, okay, later on fluid mechanics, fluid dynamic, etc. So it's quite a nice version that we're going to have. Okay, get to know it. So the question is going to be, one of them, of course, will be given. You have several of those. So there you are, example. If they ask for the differential, there you are. So you see, we solve every problem we need so far. Okay, we introduce a notion of the derivative that would be useful because it extends whatever we know in function of one variable. That's why we like it. So find the differential this time. Find the differential. So we stay with this one for a while. Find the differential of the function. See, the function would be given to you. You've done, of course, differential equation. You do quite a lot over there. And we are going to do part of those idea of a differential equation here. So that would be the sine of the xy. That's it. You want to find the differentials. You can do it right away, but I just find the differential partial derivatives first. Then I put it into differential form. Okay, so this is going to be the solution. So I'm going to use the partial derivatives, okay, respect to the x. Both of them containing x, so I have to use the product rule. You have the first times second, second first, respect to the x. You have x squared with the 2x times the second one plus, okay, second first. Sine function would be cosine, but you have to take care of the inside. If of the inside respect to the x would be y, so I get the cosine of xy, but I have to multiply by the derivative of inside respect to the x, which is y. Instead of a second, I have to multiply by the first one, which is x squared. Okay. So this is going to be the derivative. Again, I can switch it later to write down in the better format. Okay, so let's go with respect to the x, with respect to the y. So I don't have to use the product rule because the first one, there is no y here. So it's going to be a number, x squared. So I keep the x squared as is. Then I have to find the derivative of sine of xy respect to the y. So the derivative of sine would be cosine. Cosine of xy again. Then this is the derivative of a second one. And then I have to multiply by the derivative of the inside respect to the y. That give me an x. Okay, so it's not a product rule because you differentiate respect to the y. So x squared is a number, just keep it. So differentiate sine of xy respect to the y. Derivative of a sine, cosine, u prime. Derivative of inside respect to the y, which is x. So this would be simply x cubed, cosine of the xy. Any question? So give us the differential of the z. Differential of the z is going to be partial respect to the x. This is it. So we have 2x sine of xy plus, I put this one up in front, x squared y cosine of the xy times it by dx. Okay, that would be f of x dx plus the other one, it's a x cubed cosine of the xy, okay, times it by the dy. So that gives you the differential of the function to give you the result. Okay, any question? So let's have a break now. We come back, we can connect it to the one problem from calculus 1, and of course we are done. Almost done with this section 13.5. So that's the kind of motivation of the derivative of the function and a kind of differentiability. It's very classic differentiability that we have. You're going to have a couple of more types. So that will enable us to extend all the practical formulas and of course the chain rule. So have a break. I give you an application to the implicit differentiation, and then we take the chain rule. The next section we able to do both of them. Okay, any question? So it's 11:55. So let's have something like 12:10. We come back and we take section 13.5, the chain rule. So let's see if we can do both of them together. Okay, see you then. Okay, we're going to continue. Any question? So we'll talk about the differential. Okay, and so we have a kind of method to be able to find the derivative of these functions or something similar to the derivative. Okay, so one quick application of this type of ideas, it's not bad to know it. In calculus 1, you did have a so-called implicit differentiation. Just want to show you that how we can find an easier formula to be able to differentiate those type of functions. I'm not going to use it, but it's nice to know. Okay, you have a couple of problems in your book. So the remark for the differential, how we're going to use it, you get a short formula, if you like, for implicit differentiation. So remark, implicit differentiation. Implicit differentiation. It's going to be useful to know it. Previously we used the chain rule. Okay, remember if the function y is given to in a part of an equation in x and the y together, mixed together, we want to know how to find the y prime from those type of functions. So we just recall that if a function y equal to the f of x is given by an equation, okay, by an equation in terms of both variables, x and y, such that you get something like f of x comma y equal to the 0. So you have a function y, but you have to find it from this equation. And sometimes this equation, or most of the time, this equation is not going to be solved for y. So then we say the function is defined implicitly. Then y equal to the f of x, okay, is said to be implicitly defined. Okay, implicitly defined function. Define function. So that's an implicit function. So for example, if the function is given to by this equation, for example, you say you have the equation like x cubed plus y squared equal to 3x to the fourth, y to the fourth, okay, plus sine x. So if this is given to you, then y is implicitly defined. Then y is a function, y is implicitly defined as a function of x. Okay, as a function, put it here, as a function of x. So if you want to find the y prime, in calculus 1, we're just using implicit differentiation. We differentiate it using the power rule. But when we get to the y squared, derivative would be 2y prime. But the way we can do it in this course, or just using the idea of differential, is going to be this one. Note that. We bring everything to one side of the equation, and we're going to call it a function of two variables. And then we work with the differential. Okay, so this is it. We write it down as x cubed plus y squared minus 3x to the fourth, y to the fourth, minus sine x equal to the 0. Okay, so everything here, we are going to call it a z, a function of two variables. So if you call everything a z over here, okay, so what you have is the fact that, so we have a z equal to the f of x comma y. Since it's equal to the 0, so that will make it into, if you find the differential of the z would be 0. But what is differential of the z? Remember, differential of the z is derivative, partial derivative fx dx plus fy dy equal to the 0 now. Because d of z is a differential of the z. So just solve for the, we are interested in y prime. So I'm going to write it down as ey dy equal to the negative f sub x dx. Divide both sides by dx. Okay, just make it as dy dx, which is y prime, equal to, it's going to be equal to the negative partial derivative of f respect to the x over y. And you know that this is simply y prime. So y prime is equal to the negative partial respect to the x, partial respect to the y. Okay, so we get a kind of shortcut for those type of problems in calculus 1, just to remind you. And some people, they use it in calculus 1, but anytime they use, I question them. How did you find out? You don't have these partial derivatives or the function of two variables in calculus 1. But it's a shortcut. Any question? So if you want to apply it to this is it. Y prime equal to, you can put this negative in front. Derivative of f respect to the x, you see, respect to the x. This would be 3x squared, 0. 4 times 3, 12, minus 12x cubed y to the 4th, and the cosine. So we get 3x squared on the top, 3x squared minus 12x cubed y to the 4th, okay, minus cosine x. That's the top. The bottom one, derivative with respect to the y, respect to the y, 0. 2y, 4 times 3, 12, minus 12x to the 4th y cubed, and the other one would be 0. So we get 2y. Okay, we get the 2y minus 12x to the 4th y cubed. This is a kind of a shortcut for implicit differentiation. I'm not going to use it in this course. I mean, you can use it anytime, you need it, but not directly is going to be used. Okay, but you have a couple of problems in your book, and then you can use this one. Okay, any question? So that portion of a dz equal to the 0 is going to be used quite a lot, and you will see it later on. We come back to it, and to use it. Okay, so this is application of the differentials, and so we define the derivative of the function in terms of the differential, and we be able, to make it practical, and just the application. As I told you, use geometry, and it can be used in application problems. Okay, so we're done with this section 13.4. We are going to see another type of derivative. We call it directional derivative later on. Okay, but this is what we need so far. So what next? Of course, now that you have the derivative of the function or the differential, how about chain rule? Okay, so it's going to be 13.5. Let me give one question from each, one question on the chain rule, sometimes two. So what's the chain rule formula for the function of several variables? Okay, chain rule. Okay, that's it, chain rule formula. It's used in application problems quite a lot. That's it. So let's say what is going to be the possibility of the functions that we're going to have. The warm up first, we're just using that idea of a differential to make it. All the problems that we use in science, most of them are, it's like the related rate problems that you did before. You know that the function x and the y by themselves, they can be a function of the third variable t, which is time. Then you need the rate, okay, dx dt, dy dt. So this is going to be kind of type 1 that you're going to have. And in your book, they call it type 1 and type 2. There's only one type really. But this type 1, just, it's a warm-up, okay? So let's do this one first. This is the application. You don't need this one. You can do it without it. But let's see what's going to be the problem. So related rate problem. So this is, recall that. I'm going to call chain rule just the main one that we're going to have. Now, recall that, not bad to set up the formula. Recall that if y equal to the f of x, function of one variable, and then as I talk about it, x is a function of t, so x is going to be x of t, and y, that's it, and x of t, let's see, both of them are differentiable. Okay, differentiable functions. Okay, so this means that this is going to be differentiable with respect to the t. This is going to be differentiable to the x, okay? And of course, as you know that the y would be also a function of t. And then what's going to be, if you want to differentiate it, then by chain rule, by the chain rule formula, you know that the situation that's going to have is the fact that you get the y of t equal to the f of x of t. So when you use the chain rule, this is a composition of two functions. Outside function is f, inside function is x, okay? So if you differentiate respect to the t, dy dt is going to be equal to derivative of the outside function. The outside function is f function, which is like the y function. Okay, derivative respect to the x. Okay, so this is going to be kind of dy dx times derivative of the inside function. Inside function is a function of t. So it's going to be dx dt. You see, this is what you have, the usual chain rule. Okay, so it's a kind that we use in related rate problems when your variable at different time are going to be in different positions. Now, if you want to extend this one in in the function in higher dimension, if you like, the function is going to be two variable. Okay, now suppose in two dimensional, you start with the z equal to f of x comma y. Then your x is going to be a function of t, and your y are going to be a function of t. That's going to be one. If all of them are differentiable again, all of them are going to be differentiable. Then what are going to have? Then say same thing. Your z would be z of t. It's going to be f of x of t, y of t. So that's one. So if you want to copy the formula, you can talk about differential of this function now. Remember now, differential of the z respect to the t would be equal to remember in the case of the f, which is a function of two variables, we just use the partial derivatives. So it's going to be f sub x. Remember differential, you see differential of the z Let's see, f sub x dx plus f sub y dy. Now this is how we're going to use it now. F partial of the f, partial of the f, respect to the x, that's one, times the differential of the x. Differential of the x, since x is a function of t, is going to be just dx dt. You see, that's going to be one. So the first one is a function of two variables. I use the partial derivative. Or the second one, x is a function of t, function of one variable, I use dx dt. Plus differential of the y, again, the derivative of the f respect to the y. So that gives you differential of the y, differential of the f respect to the y, then derivative of y, differential of the y is going to be dy dt. You see, this is going to be kind of two-dimensional version of the chain rule. Okay, in your book, they call this one chain rule of the type 1. But, it's just ordinary chain rule, but we're just using the differential to take care of it. Okay, for this type of problem, if you then don't say chain rule, you just substitute really. If you substitute x and the y here and do the algebra, the result z is going to be a function of t, and you can easily differentiate it. But it would be good for us to be prepared for the next part. Okay, so we're just using the idea of the differential. I have to change it to format, so it's like a change. So it's going to be dt is like, if you cancel these two together, that give you df dt. If you cancel these two together, that give you df dt. This is the way you remember it. Okay, in your book they give a kind of a diagram. You don't need it really, but just explain it in case you see it. This is the way to do it. This is z, is a function of two variables, the function of x, and this is a function of y. But f is also a function of t. X is a function of t. And the f is also a function of t. So the way you can think about it, if you go from z to x, z is a function of two variables. So if you want to differentiate respect to the x, is a partial, round z, round x. And this is going to be round z, round y. Then you continue with this one. X is just a function of t, so that gives you derivative of x respect to the t, which is dx dt. And this is going to be dy dt. So this is the way you're going to create that formula. You want to find round z, round t. Okay, this is in fact round z, round t, which is the same thing. It's going to be a function of t really. Okay, so this is going to be your formula. In practice, if you want round z, round t, on dx dz, dz dt, the same thing. So I go towards this line first. It's going to be round z, round x, times the dx dt. Then you come back. That gives you round z, round y, times dy dt. Okay, now if you like this type of diagram, but you don't need it. You just think about the differential. It's a composition of two functions. That's it. Chain rule is a composition of two functions. So when you get to the first part, you have to apply the chain rule here. This is a function of two variable partial. The inside function is a function of t dx dt. Then plus, because it's a differential. You get the second one, the function is a function of two variables. It's going to be round f, round y, times the derivative of inside, which is d by dt. That give you the result. Okay, so that's a kind of type 1. And even you don't need it, I'll give you an example. You will see how we're going to do it. So let's get the example. We are interested in the second one. And we usually give you one question maybe on this one too. So because this type you can get away with it by just finding it right away. You see, look at this. You find out that it's nothing new. Suppose that we have the following. Function z, x squared y. X is a function of t squared. Y is a function of t cubed. That's it. That's a chain rule. That's a related rate types problem. If you substitute for x and the y, you get a function of t, you differentiate it. But they are going to ask you use the chain rule. Chain rule to find dz dt. Since they ask use the chain rule, you are not going to substitute first. You just find it as is. It's like a differential of the z, but respect to the t. Okay, so this is how we're going to do it. Solution. The formula first. dz dt, differential, is a function of x and the y, partial respect to the x first, round the z, round x, times the dx, which is going to be dx dt. That's the first one, plus differential. Partial respect to the y is going to be round the z, round the y, times the differential of the y, which is going to be dy, okay, dy dt. Even if you write round y, it's the same. Okay, that's your formula. Any question? Just do it. Equal to derivative of z respect to the x, 2x, 2xy, 2xy, times derivative of x respect to the t, derivative of x, 2t, 2t, plus derivative respect to the y, derivative of y is 1, so that gives x squared, times derivative of y respect to the t, t cubed, 3t squared, 3t squared. But you have to change everything into the t. You're not done. Okay, so you have to substitute, say, oh, bet x is equal to the t squared. Okay, and y is equal to the t cube. Substitute, simplify. So you arrive at dz dt, which is 2xy. Substitute 2 times x, t squared, times y, t cubed, and the times 2t. That's the first one, plus x squared, x is t squared squared, times the 3t squared. Simplified, you're done. 2 times 2 would be 4. Okay, so it's going to be equal to the 4t to the power. Add them together, 2 and 3, 5, and 1, 6. Plus, that's going to be t squared, which is going to be equal to the t to the 4th. T to the 4 times 3t squared. So it's going to be 4t to the 6 plus 3t to the 6. So you add them together, that gives you 7t to the 6. So dz dt is going to be equal to the 7t to the 6, the final answer. Okay, that's a warm-up of the chain rule. Any question? And you know that method 2 for this, of course, they ask for the chain rule, just to warm up for the main chain rule. But if this problem was given to you before, okay, let's see method 2 without chain rule. You just find it first, you see. Z is equal to the x squared y. Substitute. X is t squared, so t squared times y, t cubed. T squared would be t to the 4th times t cubed. That gives you t to the 7th. So your function simply is z is equal to what? Z is equal to the t cubed. So z prime is 7, okay? So dz dt is 70 to the 6. Same thing, okay? But just want to motivate the formula for the chain rule, really. That's why, take that one. So that was a kind of the warm-up to the actual chain rule that we are going to have. Okay, any question? Now, what is now it's going to be the actual chain rule? The actual chain rule is going to be, you see, your function is going to be z. It's going to be a function of two variables, x and the y. But x and the y, you see over here, x and the y was a function of one variable, tt. But in this case, x and the y, they are going to be a function of two variables by themselves. Okay, so we start with the z function of two variables, but x and the y are all function of two new variables. So then you apply the chain rule to that one. Okay, man, it's going to be just this one, you just repeat it. So, the book say type 1, type 2, but I'm going to call this one chain rule. And we are going to question you on this, okay? This is going to be the chain rule formula for a function of two variables. Chain rule formula. Officially, this is the one that you have to focus. That's it. So what's this version? We get a function of two variables to start, but x and the y are going to be just separate. So this is it. If x is going to be a function of two variables, we usually say u and the v. So the variable x is not just a variable, function of t. It's going to be function of two variables. If this is going to be and y equal to the y of uv, since they are a function of two variables, we have to focus on the partial derivatives. So if x and the y, as you can see, a function, they have first partial derivatives. They are differentiable, but differentiable with respect to each variable. A first partial derivatives at a point u comma v. Okay, that's it. So the partial derivative of x respect to the u and the partial derivative of x respect to the v does exist. The same thing for the y. Okay, those four partial derivatives. Now we bring a function. And if we have the function z, which is going to be f of x comma y. So z is a function of two variables, and each component by themselves are also a function of two variables. Is going to be differentiable. Is going to be differentiable at the point okay. The points are going to be, of course, you see, x of t, this is the point, x of u comma v, and y of u comma v. If this is going to be differentiable, then you are going to have the following. The chain rule. Partial derivative of z respect to the x, respect to the last variable u, and the partial derivative respect to the v. This is what we want to write. Okay, are you ready? What is partial derivative of z respect to the u, the last variable? Is equal to, is like a differential. Remember, z is a function of x and a function of y. Now you bring two new variables. This is the way we do it. Composition of two functions, chain rule. The first one, z is a function of x, so it's going to be partial of the z respect to the x. That's outside. Remember, times it by the derivative of inside. Okay, the inside function is x, so it's going to be derivative of x respect to the u. So it's going to be derivative round of x round the u. That is going to be the first part. Okay, because x is a z is a function of x. Remember, f sub x differential of the x and the y plus differential the second one. Again, z is a function of y, so it's going to be round z round y times differential of the y. Y is also a function of u, so it's going to be round y round u. That's it. You see, if you eliminate those, these dx dx, just give you dz du, all of that. Okay, it's a notion of a differential. So we start with the z, that's it. You have to find the partial of f respect to the first variable times the differential of the x, which is going to be dx du. Then you go to the second variable. So the partial of the f respect to the second variable, but the second variable is also a function of u. So that's a derivative respect to the u. Okay. Second one, respect to the y. So respect to the v. So partial of the z respect to the v is equal to z is a function of x, so it's going to be round z round x again, but x is a function of v. That's it. Plus the function z is a function of y too, so it's going to be round z round y again, but y is a function of v. That's it. So that give it the chain rule. It doesn't matter. You can have many other variables. Okay. So in this case, it's a composition of two functions. So you can have many if you like to get these true. Okay, it's easy to write. In your book, they give you, a diagram. I just write it down just to explain it, but otherwise we are not going to use it. You see, this is the way they describe it for you. This is z. Z is a function of x, but x is a function of u and the function of v. So we go right here. Then z is also a function of x, sorry, a function of y. So this is going to be your y, and y is also a function of u and v. So this is going to be u, and this is going to be v. Okay, this is it. So as you go on, you just find the derivative. These are going to be all partial derivatives. So when you go from here, this is going to be around the z. Okay, this is going to be around the z around x. If you go from here, it's x to the v, so it's going to be around x around u. So the same thing, if you go here, it's going to be around the z around the y. And over here is going to be around y around the v. Okay, if you go inside one is around x around v. And if you go inside here, so that give you around y around u. You see, this is the way it's given to you. So you see, this is the first formula that we did. Would like to get to the u. So we start from here, round z, round x, round x, round u. Round z, round x, round x, round u. Then you come back, you get it for the y. So that give a plus, this is it. Plus round z, round y, round z, round y, and round y, round u. That's when you get respect to the u. Okay, if you want to get respect to the v, this is it. Round z, round x, times that by round x, round v, plus round z, round y, times that by round v. You know, it's the same thing. But the best thing to remember it as as is, a composition of two functions. What is chain rule? Chain rule is, you see, derivative of the outside function times the inside function. Outside function times the inside function. So we start from here, you see, f of x, round z, round x. X is a function of u times round x, round u. Plus, f is a function of y, round z, round y times the differential of the y. Okay, but just whatever method you like, because you have to use it a couple of times for us on this coming test patiently. So make sure that you are okay, you are ready for it. Otherwise, it's not a big deal to get this through. Okay, any question? Now, you are going to have two types of question. The first one is a straightforward. The function will be given to you, evaluate it. The other one, there are some equations in application problems. In fact, there are some partial differential equation. You see, the equation that use ordinary derivative in it, we call it ordinary differential equation. But if you use the partial derivatives, we call it partial derivative, partial differential equation. Okay, ODE, ordinary differential equation, PDE, partial okay, derivative equation. So this equation of that format. So we just check one of them for you, and we ask you one to do. Okay, so let's get the first type. It's not difficult, you know. Mostly we make it easy for you by giving you just finding out the exact point. So that would be easier to handle. Okay, so not a big deal. So let's get one example. You need two examples, two questions for this. Okay, are you ready? There you are. Given that, and just pick the similar one for your assignment. Given that, what is that? The function is z equal to exponential function e to the xy. That's a z. X equal to 2u plus v. That is x. And y equal to uv. So z is a function of x and the y. And as you can see, x and y are also a function of two variables. So what do you want? You want to find? Okay, find round z, round u, partial derivative with respect to the u, and round z, round v. But we want it at this point, at the point u comma v is equal to -½ and 1. When the points are given to, that's the best case. And they usually give you the point. That's going to make it easier for us. Okay, first thing to do is, because the points that you need is, this is u and the v, you may need x and the y as well. So you better find the x and the y so that you be ready for all the possible substitution. Okay, so the first thing to do is find the corresponding value for x and the y. Okay, note that. So what you have the uv equal to the -½ and 1. So that make it the u into the -½ Okay, this is it, and your v is equal to 1. Go substitute here to get the x and the y. Okay, so also your x is equal to the 2u plus v. U is -½ so it's going to be 2 times -½ plus v, which is 1. So it's going to be -1 plus 1, which is equal to the 0. So you make a note that your x is 0. Okay, find the y. So it's going to be y is equal to u over v. Okay, u is negative 1/2. That's easy. That's the other one is 1. Is a negative 1/2 over 1, which is going to be negative 1/2. Okay, so your y is negative 1/2. So you keep this one. As soon as you find the numbers, you just substitute and quickly we get the result. Now start differentiating. Are you ready? Derivative with respect to the u first. Write your formula and bring them in. So this is going to be the first one. Round z, round u. The formula first. Z is a function of x and y. It's a function of x, so it's going to be round z, round x. X is a function of u. Round x, round u. Chain rule, outside, inside. Plus second variable. The same thing. Z is the function of y. So round z, round y. Y is also a function of u. Round y, round u. This is your formula. Okay, now differentiate, then you substitute, then you done. Equal to derivative of z respect to the x is exponential function. You know that the exponential function derivative would be the same, e to the xy, but you have to, it's going to be u prime times e to the y. Okay, so it's going to be e to the x times y. Okay, times u prime, derivative of xy respect to the x, which is y. So that gives you y e to the xy. Any question? Exponential function never change. So exponential function stay the same. And you have to multiply with u prime. U prime is derivative with respect to the x, which is y. Now times round x, round u. Round x, round u. This is x. Derivative of x respect to the u, which is going to be 2. So this is going to be times. Okay, times 2 plus. We get the second one. And what's going to be the second one? Okay. So the second one, round z, round z, round y. If of z respect to the y, the same thing, exponential function would be the same. U prime would be x this time, x e to the xy. So that's going to be, round z, round y. Okay, times derivative of y respect to the u, y. This is y. Respect to the u, it's just derivative of u is 1. So that gives 1 over u, 1 over v. So this is going to be the derivative. Any question? Since they ask it for those numbers that you have, okay, just substitute. Because you don't need it. You just want it at that and those numbers. So it's going to be equal to, at the information that we have. Your y is negative half. It's going to be negative half. Okay, times it. E to the x times y. X is 0. So that gives e to the 0. Okay, times 2 plus x. X is 0. So x0, just take this one. Just substitute to see what's going on. So that's it. So what we're going to have. The second part would be 0 right away because of this is 0. And this is e to the 0 would be 1. Okay. Negative 1/2. I just explained it's going to be negative 1/2 times 2. And the plus 0. So this is going to be simply negative 1 plus 0, which is a negative 1. Okay. So directly substitute when you get it. So that's it. We find the round z, round u is equal to the negative 1 at that point. Any question? So you better substitute, some people, they simplify it and then at the end they substitute. You don't need it because they ask it at the specific number. So substitute those numbers, okay, and then you get your result right away. Okay, so that was run Z, run U. So we're going to repeat it again. Repeat it again for the run Z, run the V. Okay, run Z, run V. Equal to, same thing. Z is a function of X, so it's going to be run Z, run X. And X is a function of V, run Z, run V, chain rule. Outside, inside. It's a differential type plus Z is a function of Y as well. So it's going to be around the Z, around the Y. Y is a function of V, so it's going to be around Y, around the V. That's the formula. You already got the round X, the round Z, round X from the first part. So you don't have to worry about it. So it's going to be the same thing. Okay, so that was YE to the XY. So the only new one is derivative of X respect to the V. Okay, what was the X? You see this is X. With respect to the V would be just 1. Okay, so that would be just times 1. Last round Z, round Y as we did it before. It's X e to the XY times the derivative of Y respect to the V. You see this is your Y. Respect to the V is the derivative of the top down bottom would be 0, bottom top would be 1, negative U over V squared. Okay, so it's going to be a kind of a quotient rule, U over V squared. Okay, so that the first part are going to be the same, so you don't have to repeat it. Now again, you substitute the numbers that you have to get this result. So this is going to be equal to the, your Y is negative half, is going to be unchanged, this one, negative 1/2 e to the 0, okay, times that by 1. And over here, X was 0, so everything would be 0 because of the X. Then you substitute for the U and the V. Okay, what is a U? It's a negative, U is a negative half, and the V is 1. Okay, negative 1/2 over 1. You don't need the second one because, you have the 0 here. So you don't have to worry about this one, whatever it is. This is 0. So I put it here to finish it. So the round Z round V is going to be equal to, so that simply give you a negative half. Because the first part is 0 because of this 0, e to the 0 is 1, so that give you negative 1/2, the final answer. Okay, so this is the way they give you these problems. Some of them in your book there is no number. It would be, quite a lot to write, but we just want to make sure you get the idea of how we're going to operate with the chain rule. Question? So this is a type 1 that we have. Of course, we did it for a function of 2 variables. You may begin a function of 3 variables, it doesn't matter. So you may have the x, y, z. So I just going to extend that formula. Then I give you one question of the type 2, as I told you, the type that we use in application problems in science. And sometimes you see these formulas. Okay, are you ready? So let's see what's going to be the version of the formula for the function of 3 variables. And I give you that type 2 question, and identity would be given, and you want to prove it. Okay, so let's see what's going to be the version in 3-dimensional. Then we are done with this section. So the remark, we're not going to do much about these functions. We're going to use them, of course, from time to time. So I want to make sure we are ready for it and for applications. Let's see what's going to be this version in 3 dimensionals. Okay. So if the function, so if let's say called function W is f of x, y, z. It's a function of 3 variables. and x is a function of two variables, u, v, and y. Okay, that's going to be 1. X, y is a function of two variables, and z is a function of two variables, u and v. Okay, these are all functions, are all differentiable, are differentiable. Differentiable. Is that going to be the case? And then the chain rule. Composition of two functions, you see. W or f is a function of x, x is a function of u, and a function of v. So just apply the chain rule, derivative of the outside times inside. Okay, are you ready? Let's take one of them. Derivative of a w respect to the u. The last variable, you see this the way we do it. Chain rule. Outside, inside. W is a function of x, so the derivative of the outside would be round w round x. But x is a function of u, so it's going to be round the x, round the v, round u. That's the first one. It's a differential type, so plus. Repeat it again. W is a function of y, so it's going to be round w round y. But y is a function of u as well, so it's going to be round y round u. That's the second one. Any question? But we have one more variable. We continue. W is a function of z, so it's going to be around the w around z, partial respect to the z, but z is a function of u, so that gives around z around u. That is your formula. You see, if you eliminate all those diagonal, if you like, you end up with the around w around u all the time. This must be your case. Okay, this is for the three variables. So that's respect to the u. We can copy this one, the same thing for the v. So let's repeat it again. Partial of the w respect to the v. Again, outside, inside. W is a function of x, so it's going to be round w, round x. But x is a function of v, so it's going to be round x around v. Plus. We continue, w is a function of y. So it's going to be round w around y. Y is the function of v. So it's going to be round y around, okay, v. That's the y. So continue, w is a function of z. So it's going to be around w around z. Z is also a function of v. So that gives you the formula. Okay, so it doesn't matter, as many functions you have, but at most we are going to go with the function of three variables. Okay, then a function may be given and asked for various differentiation. But as I told you, these partials are going to be used kind of a definition, an equation that you're going to have. You may see it quite a lot in physics. Okay, we call it partial differential equation. Some of them are very hard to solve, and we have different techniques to do it. So again, just want to give an idea of how we're going to operate with these type of problems, and we are going to question you as an equation would be given to you and we want to confirm it. So we give you 1 on this test, but we are not going to repeat this on the final. As I told you, these sections, the derivative, as soon as we're done, just tested once. But it's nice to know. You have a couple of them, but this is a very famous equation. Just want to how to handle this type of problems. Are you ready? What is this equation? You should look at this one. This is one of the problem in your book. Suppose they give you this one. They give you a function of this one. Suppose p is equal to You don't have the actual function. That's fun of these questions. Okay, the function is going to be called P or W, we call it P. This function is a function of U minus W, okay, V minus U, and the U minus W. You see, you don't have the function, but you know that this function is going to be of this type. Okay, whatever format is this function is differentiable. Is a differentiable function. Okay, differentiable function. Respect to whatever variable you have. Now they want you to confirm this equation. Show that. Okay, show that round P round U plus round P round V plus round P round W is equal to the 0. You see, you don't have the function, but with this information, you want to prove that this function would satisfy this condition. The sum of those partial derivatives happen to be equal to the 0. Okay. You have to check this one, set it up into the form that it's going to be easy to handle. So this is basically a function of 3 variables, but the values are not going to be directly. So what you can do is you can call this one X, this one Y, this one Z. So then P would be a function of 3 variables. Okay, so for the solution, you have to simplify the function, otherwise we can't do it. So what we can do is we can change it to the function of 3 variables, suppose 3 familiar variables, if you like. So we get X to be equal to the U minus W, Y to be equal to the V minus U, okay, and Z to be equal to, okay, U minus W. That's going to be the case. Then what's going to be your function? Okay, then your function P is going to be simply a function of 3 variables, X, Y, Z. That's your function. Now that's easy to differentiate, you see. Again, you don't have the, the other part of the function, the formula, but nothing to worry about. We can, we can find this. Okay. Now let's go for it. Find whatever, how much you can or how far you can go. Find the round derivative, partial derivative with respect to the UVW. So it's like you want to find the partial derivative of a function of 3 variables, and the variables are also function of the new variables. So it's going to be exactly the one that we have over here. You see, that is a situation that you are going to have. Okay, so just find each of these quantities and then add them together, okay, to see what's going on. Any question? So it's the way, you summarize your problem and then now you go for it. So let's find out. Partial derivative with respect to we have to find partial with respect to the U, V, and W. So we go with the U first. What is the partial derivative with respect to the U? Function, you say the P is a function of X, Y, Z. So outside, inside for all of them. So first thing to do is partial is derivative is a function of X. So it's going to be round P around X. But X is the function of U. So it's going to be times round X around U. Okay, that's the first part. But continue differential form plus P is a function of Y. So that gives a round P round Y. But Y is a function of U. So that gives you round Y around U. Okay, that's it. But it's also a function of Z. So we have to continue round P round Z. And Z is a function of U. So that's going to be round Z round U. You see, you set up your formula. and you substitute whatever you have and don't worry about the rest. Okay, so what do you have? You see, I just explained this first one. You see, this is X. So you have round X, round Y. Okay, so just remind you that you have to find these. Okay, you can find these quantities. Okay, so these quantities are round X, round U. Round X, round U, derivative restricted to U would be 1. Round Y, round U, derivative of Y respect to the U would be a -1. Round Z, round U is going to be a +1. You don't have anything else, no worry. Substitute, keep it. So if you substitute here, so the calculation going to be, so we have the round P round U is equal to, this is 1, so that give a round P round X. Okay, this is a -1 minus a round P round Y, and that's a +1. Round P, round P, round, okay, round Z. That's a round P, round Z. So this is, you see, as far as you can, you just find the round P, round U. Okay, don't worry, because if you find the other one, this quantity will stay the same. So then you'll be able to simplify it when you add them together. Okay, so that's it. That's the first part. Any question? So we have to repeat it. You find the round P, round V, and the round P, round W. You add them together, these quantities would be repeated in all of them. So when you add them together, they will cancel out each other. Then you'll be able to find the result. Okay, so we have to continue. We have to repeat this one again. At this time, differentiating respect to the V, and then respecting to the, okay, the W. But we add them together easily, you know, they will cancel out the extra terms. Okay, any question? So let's go and continue finding the other two. So now we got the idea and do it quickly. Okay, and some of them are very famous equations. Okay, so the next one, repeat it again, this time derivative respect to the V, round P, round V. Again, P is a function of X, so round P, round X. Okay, round P, round X, then the X is a function of V, plus P is a function of Y, so that's going to be Y. Y is a function of V. Then Z, round P, round Z, and the Z is a function of V. Okay, again, the known one that you can find are the following. So we go to the, okay, the version that we have. So you find the round X, round V. Remember what is the X? X was U minus W. There is no V in X. So this would be 0. It's very good. Okay, then round Y, round V. Go to Y, Y is V minus U. So that would be 1. Then round Z, round V. Remember, Z is U minus W. There is no V in it. So that's 0, which is very good. Okay, so simply this means what? This means this would be cancel out. And this would cancel out. And that's simply 1. So if you put them together, round P, round V is simply what? Is simply round P, round Y. So that is going to be the second one. And when you add it to the other one, this would cancel out also. Okay, any question? So we did the round P, round V, one more, W. Okay, already. So let's differentiate. Round P, round W. Again, P is a function of X, so it's going to be round P, round X. But X is a function of W. Differential form, so plus. P is a function of Y, round P, round Y. But Y is a function of W, so round W, round Y, round W. Because you need a W here. Okay, again, a differential form. P is a function of Z, so round P, round Z. But the Z is a function of W, function of W. Again, you have to check these. Lift up X with respect to W, Y, and Z. Okay, going back to the formula that we did have. X is U minus W. So derivative of W, X respect to the W is going to be just a -1 because X is U minus W. Derivative of Y respect to the W, go to the Y. Y is V minus U. There is no W in it. So that's 0. And round Z, round W. Z is U minus W. So that's going to be -1. That's it. So this would be 0, would be out. This last one is a -1, and this is also a -1. So what's going to be the conclusion? The conclusion is that round P, round W is going to be equal to negative round P, round X. Okay, the middle one would be out, minus again, round P, round Z. Okay, that's it. Now add all these three together, the result must be 0. Okay, let's do it. Therefore, that's it. So you are interested in what? Interested in round P, round U, round P, round V, plus round P, round W. Add them together. To see that this is 0. So if you go back and check for the first part, we get this one. This is what we have for the first part. Round P, round X. Okay, minus round P, round Y. And round P, round Z. This is what we get for the first part. Okay, in the second part, round P, round V, this is it. For the second part, I put it inside print so you know the difference. It's going to be round P, round Y. And the last one is this one. So it's going to be plus negative round P, round X, minus round P, round Z. That's it. Round P, round X would be cancelled out. This would be out. And this is it, negative PY and this one, these two would cancel out. And also the last one. Okay, and these two would cancel out. So we get a 0. And with that. Okay, so they give me kind of experience on how you handle this type of equations. Okay, it's nice because you don't have to function, but these connections would give you a result. So we give you a couple. We give you one on this next test, just to get the experience how you handle these type of problems, and you get a quite in your book, in your assignment. You just get, keep one of them. But when you get your practice one, you get the idea of the type that we are going to be interested in. There's one on that practice one. So expect 2 questions on the chain rule for the next test. One of them would be just straightforward. You differentiate it and you subset to get the result. And the other one is a kind of, equation, something, these properties. So these are going to be used in application problems. That's it, 13.5. We did the definitions of the chain rule. The next section is going to be quite different. We have no class tomorrow, and we are going to check that section on Wednesday. What is that section? It's quite interesting. You see, we did have some difficulty. We did, take care of the derivative, really nice one, and everything was in the line of the calculus one, function of one variable. We use the tangent line approximation to be able to take care of it. This next concept there is going to be, remember the partial derivatives that we did. We are going to extend the partial derivatives. We are going to extend it to something we call a directional derivative. That directional derivative would be useful for you if you have a kind of a rate of change problems. So basically, the partial, when you say partial derivative with respect to the x, it's a kind of, finding the derivative in the direction of the x-axis. And if you get it with respect to the y, is in direction, in the y-axis or the z-axis. Now the question is going to be, how about in the direction of any other vector that you like? Okay, so we nicely extended at any other vectors. Okay, that gives something very much similar to the what we usually call derivative. Again, directional derivatives are going to be used when you're talking about the values, rate of change types. But when we want to make it practical, then that differential form that we did, that would be extended and would be quite interesting. Okay, there is a connection with another topics in future. So we talk about that one, that give another idea nicely, the calculus of function of calculus one, if you like, the function of one variable. So we take care of that one. It's going to be 13.6. Then we are done with all sorts of differentiation that we're going to be interested in. Then there is going to be a concept of a kind of optimization problem, like in calculus one. Remember, if you want to find the maximum and the minimum, so what you do is you find the critical points and then use something like first derivative test, second derivative test. It's going to be similar things over here. It's a straightforward. We try to do it. If we get time, we try to do, we may stop at the directional derivatives. Okay, give you time to prepare yourself for your next test. Okay, so I posted the tentative practice test number 2 for you. Okay, and probably we go up to the, yes, we go up to the 13.6. 13.7 is something we call it like a tangent line problem. So we may stop that. Let's see how far we can go. Our plan is to finish that chapter 13 by the end of this week. Okay, then we can go to the notion of the integrations for the rest of the course, which is going to be chapter 14 and 15. Okay, that's it. Any question? So study these quickly and start working on the practice test that I'm going to give you. Okay, I'll check your quiz and and we go over if you have any difficulty on that quiz too. So the target is going to be up to the next section, probably 2 sections. Okay, what is the question about the quiz? Do you have a question about quiz? I mean, quiz number 2? Quiz number 2 would be covered everything we did. No, we don't let you use quadratic, a spherical and polar coordinate. That's our policy. Why? Because we haven't covered it. No, that's my policy. We don't want to escape from those nice methods. No. So the question is why you cannot use polar coordinate or a spherical coordinate. We don't use it. We don't use it so far, but you are going to use it quite a lot. When we get to chapter 14 and 15, it's quadratic, polar coordinate, spherical coordinate, and cylindrical coordinate forever. Okay, but I don't let you use it for continuity and differentiability. That's why. Okay, so that would be that give you an idea that you work in the. Otherwise, you will lose some nice ideas that I talk about it. Larson, it is when you take the calculus with the Larson book, they talk about it right at the beginning. But if you take any other calculus book, they talk about it later. Okay, that's why. Okay, any question? So just try to use those nice methods that we talk about. Don't worry, you see so much in chapter 14 and the 15. Okay, it's okay, you can use it, but don't use it on the test. Especially if you want to find the limit of the function does not exist or does exist. You will lose those nice application of the rectangular coordinates. That's going to be useful for the latter part of the course, or just study this. Okay, don't use it so far. Okay, any question? So have a good one. Again, if you have any question on the test, you can arrange a Zoom meeting, then I can explain it to you. It would be not easy for me to scan all of them and send it back to you. That's why. Okay, have a good one. Happy 4th of July. Okay, have enjoyed it. No class tomorrow, and see you on Wednesday. Bye-bye. Thank you.